Math is like literally almost wait, guys, do you know the PRS thing? That's how many people do better than that.
It's basically that percent, the number.
I tried reading this thing, but I'm not sure all these numbers don't make sense.
They score better than that percent of people.
Holy Jesus
You
Christ.
guys say you're B. B?
No way. B? Oh, dude. Sorry, I thought you meant class F.
Hello, there's a couple. Good morning. See who's there. Say hi.
Hi, Jack.
I hope so.
I saw Jack Fogle. You better be on time.
Schools where it's like, okay, I'll let you take the same test you took today if you want to do it. It's like,
I'm not going to ask. This class is starting. I was going to ask something, but it's fine. Doesn't matter.
Okay, let's begin. Where's my lady?
Oh God, physics. I don't like.
I like physics. Physics is a fascinating.
Okay, so let's go ahead and begin. Let me see who I've got at home so I can check in some folks for online, which is great. Thank you for joining me, Inessa
Oh my God, Vanessa.
and Isaac,
Let's go!
Corsine,
So Isaac actually made it to a live stream.
Isaiah. It's nice. See, you have a lot of fans here, my folks at home.
Yeah.
Everybody's cheering you. That's great. Okay, so I got you four. Let's hope some others join us. So what we're doing today, everybody, is I got to look back because B group, the ones that were there last week. Yeah, there's Jack. Hey, thank you, Jack. And Matthias. Good. Good. Last week we only. So it's good that we're going to just separately talk about some of this. Good. And I now have Felix and Anton as well. Thanks everybody for joining me. That's about everybody, I think. That's great. Appreciate it. So, ooh, that's a little weird. Okay, so we did generator. So we're going to do the motor now. Okay, so here's what we're going to do today. All right, our objective, so everybody here can see it at home. Motor effect. And compare with the generator effect. Okay, so we're talking about all these things have what two forces? What two forces that are kind of combining? What's combining in this unit? U force and V force. What did you see? Well, you guys 2 weeks ago, I guess. Although you might have seen some online. What's one of the forces that's kind of happening? Magnetic. So we got magnetic forces, and maybe somebody at home could join. We got a couple more joining me from home too. So at home, folks, magnetic, and what's the other part of what we're studying? And I'll write down a couple others joining us. This is very good. I've got Jake. I've got. Oh, Jake, you don't need to be here. This is for 9E. I see Jake this afternoon. Okay, I've got Devante. And Isaac has the other one. He says, and so does Jack. He says electrical force. So we're talking about magnetic, electric. In fact, we put it all together and call it what word? Electromagnetic. Thank you. Good, exactly. The internet was slow. Okay, well, I hope it's fast enough I'm trying from your room to live stream. And Laxi, Devontae added as well, electromagnetism. Good. So we're going to see another example of that now, both folks here and folks at home, if I can arrange it carefully. I brought my magic little cart. And here we go. Out of breath already. So here's a power source. So this is different than last week because last week you might have saw that we got some electricity from doing something ourselves. Today I'm going to use electricity, so I'm going to plug this in down here on my power strip.
Didn't we use those in
I hope so.
We both having flashbacks. Yeah. Oh my God, nobody asked. You're gonna clarify for
Okay, good. So here's my power source. Folks at home, we're going to write this in a bit. For now, you're going to focus on what's happening here. Here's my power source. And folks at home, what is that? You can type in if you know what that is. Folks here, what is this? You've seen these before, seen it. It's a compass, right? Let's see if folks at home recognize that as well. What is that thing, folks at home? Yeah, that is exactly right. Now, if I hold it in my hands and let it kind of, if I hold it in my hands, somebody knew that? Yeah. Isaiah knew that, as did Jack, Isaac. Thank you. Yeah, we got a compass. It's going to orient with what? If I just hold it here. Alicia, what's it going to kind of orient with? Yeah, it points to north. Why? Ethan? Okay, so it's a magnetic pole. So the North Pole isn't just where we got Santa Claus. North is actually part of a big, huge magnet. How big is the magnet? Hannah, how big is the magnet? Big, yeah.
It's epically big.
Yeah, it's epically. It's the size of what? Earth. It's the planet Earth. So this is going to align with the Earth's magnetic field, and I'm going to let it do that. Okay, think about where you are on the building. Point to North Berlin from here. North Berlin's kind of which way? Which way is north? Okay, so North Berlin's like this way. So for me, I'm going to hold this up so you can see it. And I'm going to keep my finger there. It's pointing this way. There's a silver arrow. And for me, that's north. I'm going to put it back down and let it get happy and comfortable with the Earth's magnetic field. Okay, so now we're going to add something to this. I got a lead. So I got a single lead, and I'm going to put this on here and put it into my, make one circle, one big circle, put the negative and positive side in. Okay, Hannah, I'm going to have you move up here, and Alicia, I'm going to have you move up here. Bring your stuff now. Thank you. It ain't a punishment. I just want you to see what's going on, and obviously you can't, like right here would be great. So you can move the chair over if you want, if you're not. Either one, either one. If you want to be there, that's fine. Maybe you go to one spot, one more spot, Alicia. Thank you very much. Good. Okay, thank you. All right, so here's my compass. Here's my lead, and I'm going to have all of you see this because folks that are here, you need to stand or move around so you can see this spot. So move around. Folks who are at home, I think, can see it well enough. Try to give each other space, but I'd like you to try and get so your eyes see this spot. Okay, ready? I'm going to turn the power on. And I'm going to turn the power up and down. Let's see if folks at home can see this. Yeah, they can. So I'm going to turn the power up and down. I'm holding this next to the needle on the compass. Not real exciting, huh? It moved, but not much. So I'm going to move it to the middle amount of current. So I'm going to give it more electric current. And we're going to try it again. Oh. And I'm going to give it even more current. Now I'm going to give it enough so I hope even the folks at home can see this thing. Whoa. Exactly. We're going to try it. You ready? Ideally, if I do this just at the right moment, you ever have somebody on a swing and you push them at the right moment? What can you make them do? Kai, what can you make them do? No, they don't flip. What can you make them do?
That's always my biggest fear as a child.
Can you open that scene and just prop it open with a chair? No, what do? I push somebody right at the right moment. What happens? No, they don't fall off.
They go higher.
They go higher. Isn't that the point? Duh. Come on, you guys are little kids.
It's not really overcomplicated.
They get higher,
Don't
right?
have fun. I mean, like 40 seconds.
Okay, so
So
thank you.
you are.
So could you stop, please? This ain't the easiest thing I'm doing here, and with a whole lot of chatting, it don't get any easier. But really concentrate on what's going on here, okay? All right, so if I turn the current on, something's happening that's making this wire or making this needle push the other way. What must be happening? First off, what's going on in the wire probably? Folks at home can answer too. What's going on in the wire if I turn this current up? Aslan.
Well, you're sending electrons moving, or you're moving the electrons in the wire.
Okay, so I'm making the electrons move in the wire. Okay, so somehow that's affecting this needle, this metal needle. So even though we haven't maybe talked about it yet, if I make electrons move in a wire, what must they be creating that's screwing up this compass needle? Must be making, Isabella? A magnetic force. So they're making their own little magnetic field, and that screws up with the Earth's magnetic field, doesn't it? And which is more powerful, at least while I'm changing it. Yeah, this one, right? Because it makes it move, doesn't it? So it creates a pretty big force. And now, that's why I was saying, if I hit it at the right time, and if I adjust right, I could almost make it go and do a 360. I can't do that, but we'll see how you could do that. What if I turn this lead over? What's going to happen now when I try and do the same experiment? Do a little predicting for me. Seen it? Yeah. Yeah, say it one more time. Yeah, so the needle's not going to go not away from the lead, but sure enough. In fact, I'm getting that one really, for whatever reason, easier than this one. Maybe I got to hold it a little higher to do it the other way. So I can really get that sucker going if I just turn it at the right time. I'm going to let it stop, and I'm going to go back to pushing it instead of pulling it. Now, what was a push or pull in physics again? A push or pull is a push or pull is a what in physics? Aaron?
A force?
A force. So I'm creating a force, aren't I? Because I create a magnetic field, as Isabella pointed out. So I'm pushing it. Watch when I turn it up, and then I don't move it. Well, two things. What did you notice? It's not in its original location. That's where it was originally. So when I push it up, it does sort of, we say, deflect it, but does it keep going back and forth? No. So what do I got to do with the current to make this needle go back and forth? I got to do what with it? I can't just move it one way, I've got to,
The other one.
yeah, I gotta turn the current up and down. So if I turn it up and down, I can make this thing, so I gotta change the amount of force that I got here. I gotta change the magnetic field that I'm creating. And somehow I can do that by turning the juice, the current up and down. Or if I do it the other way, let's see if I do that and I just hold it. Yeah, so now I pulled it over, that's kind of what Asina said. But if I put it off and on, I can pull it even harder if I go with the momentum, right? Go with the flow, right? Go with the momentum. Okay. Exactly. Jack was there, so he knows this. Thank you, Jack. And Alessandra, that's right. It will move in the opposite direction. Oh, I don't need the clap. Okay. Now, folks, my question. What if I could make this go all the way around? Either that way or this way. Why is that useful? What sort of device or devices does society use that makes something go like this? Can you imagine something? And there's more than one answer. Ethan? What part of a motorcycle? The wheel. But of course, that's not driven directly by this system. Yin?
Or like the thing generator that does the turbine.
That's kind of the opposite. They're run by steam or by wind.
Oh.
So what we did last week is we generated electricity by using more or less a turbine. But this, I'm using electricity. I don't get it out of here. Ooh, it's getting really warm. Because I've got a pretty high amount of amps, don't I? It makes things warmer. Like your toaster uses a lot of amps because it gets really warm. This time I'm using electricity to make something go around. Yeah, Jack says a 360. So if I can have it do a 360, what is that? It's not the generator effect, but it's called the motor effect. So I've created a motor. Oh, I've got something that does this. Can you think of any things that use motors that make something go around?
Maybe a car motor?
A car motor. Good. What other sort of motors go around? Not like the wheels, but actually the motor itself.
Plane engine.
A plane engine, the old kind, right? A propeller?
Yeah.
Not a jet, but a propeller in a small plane. Exactly. That's a motor. So that uses electricity also creates a magnetic field and makes something spin. Anything else? Yeah.
A helicopter? Would it be the?
It could be the helicopter, the turbine, the upper blade of the helicopter, probably both of them, to be honest. What about something you might use in the summertime if it gets hot? Something else that has a motor in it. That? A fan. Exactly, Hannah. So if I got a fan with something going around, inside that's changing electricity to movement. Last week, we started it. I know we didn't get very far. We use movement to make electricity. Motors use electricity to make movement. And this is how, right? They generate a field. Good. And that causes something to move, doesn't it? Yeah. Good. All right. I want to write a couple things about that. Write a fan. We knew that. Thank you. Devontae knew that. And Corsine. Thanks for participating. Let's write a little bit of that on the board. And I'm going to let this cool off a bit. We're going to come back to that. But for now, let's talk about it. It's called So what we did again is we used to make So what were we just saying? Somebody remind me so we don't lose it. We're using here, or somebody at home, we're using Felix, we may not have gotten to that with you. We're going to show you that and remind you that in a moment. Okay, so stand by, Felix. But for now, we've used with this demo to make. Hi. Thank you. To make. So now let's answer Felix's question. Part of our goal this hour, and we'll see how far we get, is we want to contrast or compare with the generator effect. Now, I know some of you saw this and some of you did not. And Anton, I'm sorry, you may have to watch some of the video later. I'll try and, yeah, I'll save the video and send it to you, everybody. Okay, so. Let's review the generator effect. How many of you did we get to that part? Ayala, did we get to the generating electricity or not at all? You don't remember, okay. Did we use this big thing?
Oh, yeah, we did.
Yeah, because I know like Jack, you saw this, but I think others did not. So here we go. Okay, so we're going to review this, and I'm going to pull them back a bit so they can see this. This time, I have no electricity, okay? This is not, I feel like a magician. See, no strings, okay? I'm not combining this with the power source. This is going to my computer. That's not going to this. And I got a single lead on here, and I got this in millivolts. And I want to have it in that's just 1 millivolt, okay? And I'm going to turn it off and turn it back on again just to reset it. Okay. And I got a really big magnet. Okay, I don't want this anywhere near my monitor, but I do want it near this. Okay, here's what we're going to do. I'm going to take this wire and I'm going to put it through here. So, did we see this? Yes, yes, no, no? We did. Okay, so here we go. Oh, okay, that means I'm generating, electricity. Okay, so, and do we get to Faraday's law? If I make more loops, what happens? More electricity. So now, let's just kind of contrast. And I'll write this here with you. Make sure they can see here. To make. One person knows. Let's see some others be ready to fill in the blanks. And another. So what did you just see? Using
Use movement to make electricity?
Exactly. Oh. So I made the movement because I had to move the wire, right? And we made electricity. That showed on our voltmeter, that's for sure. What happened? Like I said, for a big city, you just need like 100 million monkeys in a warehouse doing this, right? Cruelty to animals, sorry. Okay, so I want to introduce, let's put some arrows. In both effects, we have three things. Three things. In both effects, we had three things. So see if internet folks, can you punch in what was common in both effects, both the motor effect and the generator effect? Folks here as well, let's now start to listen. What's one thing that was common in both, Ethan? Electricity. So we had, let's call it an electric current. In one of them, we formed it, right? Because Hannah said we made electricity. And the other one, we used it. We used electricity to make something move. If you think about it, when I made the little compass needle move. Isabella. Yeah. Let's call that, we need to have a magnetic field. Put that in there. Magnetic field. For this one, obviously magnetic field is here, right? When I did generate electricity, I got a big flipping magnet. For the other one, I actually had two magnets, didn't I? The first one is the one that held this company needle, and that was just the big magnet we call Earth. But then I made another magnetic field when I had current flow through the wire. And that's what then pushed the needle or pulled it back and forth so I can create or have a magnetic field. Good. Let's see if somebody at home gets the third thing. Ah, you got it. So I think Alessandra has the third thing, and that's movement. And I'm going to add, Alexandra, movement of what? So what thing do you got to have that's going to be moving? Hint. This has got it, and this has got it. So what's in Zena? Yes, in true, electrons. In what sort of material? What's in there, and what's this made of? And metal. So now let's describe that. So we're going to move electric charge, which Zena correctly called electrons, in a piece of metal. And the piece of metal, we used a wire or a lead. Okay, so the reason I'm being so careful with everybody here is we got a really important force named for, who else? A famous German scientist. And it involves these three things: electric current, magnetic field, and movement of the electrons in a piece of metal or in the lead. And that force, I'm going to put on the other board here. So let's have you guys take a look. Oh, not quite that force. But a pretty good force. Okay, here it is. Unfortunately, I got hungry, so I ate some of the paper there that I'd written on, but I'll use that for another class. But that's where I need that. So I'm going to give you a couple definitions of it. The name of this force that either can make electricity in a generator or movement in a motor is called the Lorentz force. So here's how to spell Lorentz force. Okay, Lorentz force is an electromagnetic force and I'm gonna define this. This is so important, but a little a little hard to grab, like a greased pig, like an eel, like a like a peanut butter sandwich. No, not a peanut butter sandwich. Like an oily something. Anyway, this is a little slippery, so I'm going to try and describe it in a couple of different ways so we understand really what the Lorentz force is about. Okay, so to start with, that it's electromagnetic force, and we're going to say it's a force on a charge, and usually we're talking about the charge being an electron. So it's a charge in the direction of an electric field. That's when I turn on the electricity in the motor effect. And I'm going to put a little spark here. You see why? And a force at a right angle to a magnetic field. Okay, my little star up there. When I talk about the electric field, the greater the electric field, or charge, the greater the force. I know this is a lot of writing. Bear with me. We're going to get to more fun stuff. We really will. But we got to write a little bit to really get our brains thinking about this effect. Yes, Inessa says, can you move this closer? I'm going to put them over here. Let's see if they can see better. Okay, Inessa, here you go. Let's see if that works without me destroying my laptop. Okay. Okay, I hope that's more readable, Inessa. Thanks for telling me. Whew. Okay, so let's read what we got so far. So Lorentz force is an electromagnetic force. We've seen it now in action two different ways. It's a force on a charge, an electron, in the direction of the field. So when I turn it, the electricity is going in a certain direction. And it's a force at a right angle to a magnetic field. We'll talk about the right angle in a moment. And that electric field, I got it right here, the greater the electric field or charge, the greater the force that happens as well. Good. Almost done. Here's an easier definition. Or the Lorentz force is a force on a charged particle due to electrical and magnetic forces. Due to electrical and magnetic forces. And that's helping. Thank you, Inessa. Okay, so that's a little easier for them to see. Hopefully you guys can still see too. Whew. So, that's not
Is that why whenever we ask that, it's there's like a blue laser thing, whenever you put the magnet to it, it's like perpendicular?
super, exactly. So when you and I had the cathode ray tube, which I since put away, there were electrons going like this, and suddenly you guys used the magnetic field, and when you did it, they didn't go like away, they went up or down. So I put the field like this, and they went whoop, or whoop, whoop, whoop. So they were at a right angle as well. Yeah, so as long as you remember that correctly. I'm gonna go like yell my brains out. Hold on.
They're just like bigger bus.
Oh my God, laughing, what a fun.
I hate being interrupted and clapping 10 times, this is 10 times more than I am. Okay, let's look at this a little bit. Okay, we all right? Okay. I want you guys to see this a little more, so hold on. Come on over, don't be shy. I'll try not to have, so you don't see anybody here, but I want you to see this again. Okay, so, notice two things. Oh, you can't see this. That's not good. I need everybody to see it. All right, have cheating Christmas. I know you did. But the reason I want to review it is I don't think we got to this part. Let's find out. Okay, so. I don't want that to fall off the desk. It's worth a lot more than me. Is it still working? It's still working. Okay, so check out some angles. This is a very geometric thing I want to show you. So if I stick this down, okay, for starters, let's call this north and south. And you guys probably know a magnetic field goes from north to south. Did you know that? Okay, so it's going this way. All right, folks at home, so it's going that way. But when I put the field in, it's at what angle to that? 90 degrees. See that? 90? I got my fingers to the way. You get the idea, right? That's 90. Okay, then I got another thing that's 90. Ready? Here's the wire, and we said we're making the electrons do what in the wire, huh? If I could see them, what are the little electrons doing in this wire when I do this business? Moving. So they're moving in the wire, and they're either going what? This way or this way, right? Let's say I move it down and they're going this way. Well, if I move it down, and here's the field of the magnet, what angle is that? Also 90 degrees. So what we got is, and this I don't think we did with you last time, I got a 90-degree angle here with the wire. I got another degree that's going here with the movement. So it's like this. Eh, eh, eh. Like this. Or if I can do it closer, can I do this? Oh, that's the way I want to do it. So I got this way, that's the magnet. I got this way, that's the electricity, the moving electrons, as Hannah said, in the wire. And I got this way, my thumb, that's the movement up or down. I want you to know that this is 3 directions. In math class, I know, why are we talking about that? In math class, what axes do you have that you write on paper? What axes, guy? X and Y. Guess what you're going to get in 10th grade? X, Y, and Z. Can you guess now? Why do you need 3 axes for real life? Not just for physics class. Because we live in 3 dimensions. And it turns out this Lorentz force is very much in 3 dimensions. So what we need to write now to add to this is that idea that whoa, the flow of electrons, the movement of metal mental, if I can spell it right, mental, and the magnetic field are all at right angles. I'll say 90-degree angles. I find that really kind of amazing and cool. Okay, and I just wrote where they can't see, so let's move that over where they can see that for a sec. So, whoa, the flow of electrons, the movement of the metal, and the magnetic field are all at 90 degrees. And the way we're going to show that is X, Y, we're going to imagine that's 90 degrees, like you're looking at your paper funny. I know, don't freak out. First time ever. Z. So look at what I got. I got 90, 90, and if you're really a 3D thinker, watch this. Whoa, whoa, okay? Isn't that crazy? So you got lots of 90-degree angles. So the flow of the electrons, the movement of the metal, and the magnetic field are all 90-degree angles. And if you do like this with your fingers, it's called the right-hand rule. You may have to memorize it in 11th or 12th grade. You don't for me. But one of them will be the magnetic field direction, the flow of electrons, and the movement of the wire. So all three of those things, it's like a fish, isn't it? So magnetic field, flow of the wire, movement of the metal. All three are at 90 to each other. So if you can kind of point with your finger like that, try that at home, right? Then you got the idea of the Lorentz effect. That's what it is. It's those three things all kind of relating to each other, all right? In an advanced class, you'll be doing that. You'll be using this, it's called the right-hand rule. And you actually can physically, without even doing the experiment, figure out, okay, if I move it this way and the current's this way, then the magnetic fields must be this way, north to south. Or you can do vice versa or whatever, you know what I'm saying? Can I put my hand down now? Yeah, okay. Okay. Now, I think all of you now at home and here have seen the two effects, right? The generator effect and today the motor effect. Do you see that they're, do I have it in my pocket? I do. We say in English, the motor effect and the generator effect, they're two sides of the same coin. That's really the way I want you to think about it. So both these effects we've had, and they really are I'm not usually a big giant fan of like of like sayings, but this so exactly matches what is really true in the physics that the generator and motor effect are really like two sides of the same coin. They both involve two different pictures, but really you end up using the same three things: electric current, magnetic field, and some sort of movement. All three are in both of these things: the generator to make electricity, or the motor to use electricity and make something spin. Ute. Questions from you here or folks at home? Okay. Especially at home. Are you guys still there? And can you see all this? I hope you can. I hope you can. My poor 9E, because I didn't see you last week, and I feel like we got a little behind. Okay, what we're going to do is give you something. My 9E. If I got it. which in all my cleverness, I may not have actually done. Let's put you back down here for a sec. Let's see if I got in this part. I don't include that's all template. I did bring it. Here it is. Okay. Folks here and at home, do you have this sheet yet? No. Folks at home, do you have this sheet? Inessa and others? Does it look familiar? If not, I'm gonna scan it and send it to you over Google Classroom. So do you have this? No, says Inessa. Okay, so I'll give you this next time. We don't need to do it this second. Because we're about out of time. Let's just chill for a minute. That's really enough for Monday. Kind of a lot. Okay, for folks at home, I'm going to say we're going to give you that sheet through Google Classroom. Thanks for joining me, and we'll see you Wednesday? No, we'll see you Thursday, okay? Thursday morning. Thank you. Bye-bye.